Electrochemistry. Electrochemical processes are oxidation-reduction reactions in which the energy released by a spontaneous reaction is converted to electricity, or electrical energy is used to cause a non-spontaneous reaction to occur. Consider this reaction. 2 moles of magnesium plus oxygen yields 2 moles of magnesium oxide. The oxidation states for magnesium and oxygen are 0. In the magnesium oxide, magnesium is 2 plus and oxygen is 2 minus. The 2 moles of magnesium are oxidized to 2 moles of magnesium 2 plus 4 electrons. This is the oxidation half reaction. The oxygen is reduced by the 4 electrons to 2 moles of the oxide ion. This is a reduction half reaction. Redox stands for reduction oxidation. A reduction oxidation reaction, such as zinc reacting with copper ion to form zinc ion plus copper. Zinc becomes oxidized to zinc 2 plus 2 electrons. Copper becomes reduced by picking up 2 electrons to form copper metal. The reducing agent is zinc. It became oxidized. It causes a reduction. The oxidizing agent is copper 2 plus. Copper 2 plus was reduced, causing an oxidation. Let's review oxidation numbers. The definition is the charge of the atom would have in a molecule or in an ionic compound if the electrons were completely transferred. First, free elements have an oxidation number of 0. In a monatomic ion, the oxidation number is equal to the charge on the ion. The oxidation number of oxygen is usually -2. The exception is peroxide, when oxygen is -1. The oxidation number of hydrogen is +1, except when it's bound to metals in a binary compound as a hydride. In these cases, it's -1. Group 1A metals are always +1, Group 2A metals are +2, and fluorine is always -1. Remember that the sum of the oxidation numbers of all atoms in a molecular ion is equal to the charge on the molecular ion. Let's identify the oxidation numbers of all of the atoms in HCO3-. Again, oxygen is -2, hydrogen is +1. We have to figure out what do we need to add to make the total charge -1. So 3 times a -2 plus 1, carbon then is +4. Let's balance these oxidation-reduction equations. The oxidation of iron 2 plus to iron 3 plus by dichromate Cr2O7 2- in acid solution. Write the unbalanced equation for the reaction in ionic form. So iron 2 plus Cr2O7 2- yields iron 3 plus chromium 3 plus. Separate the equation into 2 half reactions, the oxidation and the reduction. The oxidation is iron 2 plus becomes iron 3 plus. The reduction is Cr2O7 2- becomes Cr3 plus. Balance the atoms other than oxygen and hydrogen in each half reaction. So Cr2O7 has 2 chromiums, so we have to put a 2 in front of the Cr3 plus. For reactions in acid, add water to balance the oxygen atoms and H plus to balance the hydrogen atoms. Cr2O7 2- yields 2 Cr3 plus 7 waters. 7 oxygens in the dichromate are balanced by the 7 oxygens in the water molecule. To balance the hydrogens now, we have to add 14 hydrogens, 14 H pluses. Add electrons to one side of each half reaction to balance the charges on the half reaction. So for the iron 2 plus becoming iron 3 plus, we have to add 1 electron to make the charges equal. For the dichromate, we have to add 6 electrons to balance out the electron change. If necessary, equalize the number of electrons in the two half reactions by multiplying the half reactions by appropriate coefficients. Notice that we have 6 electrons in the reduction and 1 in the oxidation. We have to multiply the oxidation half reaction by 6. Now we just have to add the two together. Add the two half reactions together and balance the final equation by inspection. The number of electrons on both sides must cancel. The final answer is 14H plus Cr2O72 minus plus 6Fe2 plus yields 6Fe3 plus 2Cr3 plus 7 waters. The best way to do and understand redox reactions is to balance a whole bunch of them. Just practice. We will do some in class. Electrochemical cells. A galvanic cell is one that generates electricity, like a battery. An electrolytic cell generates a chemical reaction, as in plating. Here is a diagram of a galvanic cell. It has a zinc electrode immersed in a zinc sulfate solution, which provides the zinc 2+ ions. On the right-hand side, we have a copper electrode in a copper sulfate solution, which provides the copper 2+ ions, and connecting to the two is a salt bridge, which is a gel filled with potassium chloride to allow the electrons to move from one beaker to the other beaker. At the anode, we always find oxidation. So the zinc becomes oxidized to zinc 2+ plus 2 electrons. At the cathode, we find reduction. Here, the copper 2+ picks up 2 electrons to be reduced to copper. So in this case, the zinc electrode is going to slowly dissolve, and the copper electrode is going to get thicker and thicker as the copper plates out. The spontaneous redox reaction has a net reaction of zinc plus Cu2+, yielding zinc 2+ plus copper. The difference in electric potential between the anode and the cathode is called the cell voltage, sometimes called the EMF or electromotive force, or the cell potential. They all mean the same thing. Notice that in the cell that we were looking at before, the copper sulfate, zinc sulfate cell, it generates 1.10 volts of electricity. In this cell, copper 2+ is 1 molar and zinc 2+ concentration is 1 molar. We can also write a cell diagram showing this. Zinc in contact with zinc 2+ 1 molar, and then the double line is a salt bridge. Copper 2+ 1 molar in contact with copper. The anode is always written on the left, the cathode is always written on the right. The lines indicate a phase boundary, and the double line indicates a salt bridge.